Okay, so today we'll continue more examples on the Lagrangian mechanics. Okay, so before we move on, okay, so just want you to take notes on the typos that I have found on this slide. Okay, so the lower limit over here should be pi, not pi over 2, right? Because when you're in the middle, right, so you have done half rotation. Okay, so that is pi, not pi over 2. Okay, so another thing is that for the equation of cyclops, okay, so the first in the first chapter, okay, so when I draw the cyclops, the edge is touching the 0, 0, right? So, but in this case, I actually make the coordinate system such that the edge of the cyclops is not at 0, 0. So therefore, here I should minus shift it by some distance. Okay. Okay. So today, as I mentioned last time, I will first work on more examples. Okay, on the Lagrangian mechanics. Okay, and then we'll move on to well, still chapter 2, but the part 2 of the chapter 2. Okay. Okay, so you may open this lecture notes. Okay, this supplemental examples for this chapter 2, part 1. Okay, so we'll have 3 examples over here. Okay. So let's do the first one. Okay, so the setting of the first one is like the following. Okay, so I have a table over here, a fixed table, right? So, and then just what I have is that I have drill a hole. Okay, so at one point of the table, right, so that I can actually put a string through the hole. Okay, and then at the two ends of the hole of the string. Okay, so the lower end, I have put this big mass, okay, capital M, okay, and then the other small mass, M, small m, is put on the table, okay, so it's just supported by the table. Okay. And then the total length of the string is L, so I assume that this is an inelastic string, okay, so the total length is L. Okay. So what happened is that this small mass M, okay, so it's free to slide on the table, okay, without any friction, okay, but you have to remember that it's always pulled by the string, okay, because the string is basically used to support this big mass M over here, okay. So because the whole thing is under constant gravity, okay. So therefore this M, I have this weight mg. Okay. Okay, so the goal here is to set up the equation of motions. Okay, so by first finding the Lagrangian of the system. Okay, so here you can imagine that for this small m. Okay, so it's convenient to use this r and theta, okay, as the generalized coordinates, okay, for this small mass over here. Okay, so you can do circular motion, right? So, but you could also imagine that if this mass is really very heavy, right? So if the centripetal force, right? So really does not balance the weight of the mass, right? So then this mass will actually fall, and this R over here can actually change. Okay, it does not necessarily have to stay on this same circle, right? So the R is free to change. Okay. So then now if I'm going to find the kinetic energy and potential energy, so to find the Lagrangian, right? Okay, so then first of all, you may ask, okay, what about the position of this big mass here, right? So I also need another I should also need another coordinate for this, right? So for example, I need to know, basically, I need to know this distance over here, right? Right, because to describe the height of this mass. But well, because you know that the total string, the total length of the string is always L, right? So once you know that this distance is small r, then this part must be L minus r. Right? So therefore, just r and theta, the two coordinates, okay, so are enough to describe the entire system, right? Right. So that the other way to think about it is that now for this particle, right? So you have two coordinates because it's moving on the plane, right? So you need two numbers, right? And then this mass over here, obviously, it only move up and down, so you need one more. So in principle, you need three. Okay, so but because of the constraint, which is the length of the string is always a constant, so you end up just need two coordinates. Okay. So kinetic energy, right? So this one, since we use polar coordinate, right? So of course this one 1/2 mv square, and the v is written as r dot square plus r theta dot square, right? And the other one, right? So this, the movement of this, right? So it's again is 1/2 big M v square. So what is v for this big M? Right, so the v over here is the d dt, this distance L minus r. Right, so that's why the v is actually minus r dot. And therefore, the kinetic energy for this big mass is 1/2 m minus r dot square, that is just r dot square. So that's the kinetic energy, right? And for the potential energy, right? So the potential energy, we don't need to worry about the upper mass because it's always just stay at the same plane. So vertical, it does not have any vertical movement, right? So you just need to consider the gravitational potential energy for this big mass over here, right? So therefore, I have this term right here. So why is it not a minus? So we always need to be careful. Okay, so because again, right, so if I consider at this level, the gravitational potential energy is 0, right? So then because you're below, then the gravitational potential energy of this mass over here is actually minus mg L minus r. Okay. That's why you have the minus u, then the minus cancel with this minus. So that's why you have a plus mg L minus r. Okay. So once you have written down the Lagrangian, of course, what's following is the basically you don't need to think of anything else but just applying the Lagrange equation, right? So the Lagrange equation, again, just to remind you, right? So it's this. And the other is this. So with these two, you obtain these two equations. Actually, okay, I should have reversed the order. So this one gives this one. Okay, this one gives this one. So, and actually, if you look at the first equation over here, actually, this is equivalent to the conservation of angular momentum for the small mass. Okay, if you look at this equation, right? So this angular momentum, right, is this mr square omega for this small mass, right? So the d dt, this mr square omega is 0, right? So that means that the It's basically saying that the angular momentum of this particle up here is conserved. And this is, of course, not surprising to you, right? So because the force, the tension is always pointing to the origin of the coordinate system. That's why it does not produce any torque, and that's why it does not change the angular momentum of the particle. Okay. So actually, from the first equation, right? So because of the conservation of angular momentum, that means I can write this ml squared theta dot as a constant, right? And this j, of course, means the angular momentum. Okay. And how do you obtain this j, right? So you can basically just rely on the initial condition, right? So if you initial condition, I give you the initial r and the initial theta dot, right? So then you can calculate the initial angular momentum, and which is also the angular momentum of this particle at all times. Okay. So now if you have this, and you can just substitute this equation to the next equation over here. Okay. So then that's how you get an equation that only depends on r. Okay. So it describes this radial motion. So in principle, right? So you can obtain r as a function of t, right? So this one I don't know how to do it analytically, but you know that in principle you can solve it at least numerically, right? So, and of course we can also consider a special case, right? A special case that is when the r double dot is 0, right? So I believe for that you might have learned that special case when you learn about circular motion, right? So that's the case when you have exactly this tension, right? So providing the centripetal force exactly balance the weight of the mass, right? So that is, right? So if it is actually staying on a circle, right? So doing a pure circular motion, right? So what you have is you may have learned that the centripetal force, right? So it's mr theta dot square, right? And if it is exactly just balancing the weight of this, then you have this. Right? And this equation, okay, so you should be able to find that would be equivalent to say that it's equivalent to this equation by setting the r double dot to 0. Okay. So that is this equation over here should be equivalent to this one equals 0. Right. So, and this is how we do it using Lagrangian, right? So, and if we just go back to the Newtonian way, right? So that's also in this example not too difficult, right? So because all you need to do is to find out the radial component of the force acting on the particles and the transverse component, right? So, and for the small mass, right? So the only force that's acting on it is the tension in the string, right? So here I write this minus t. Okay, this minus t equals m times the acceleration in the radial direction. And then on the other hand, right? So the balancing the force acting on the mass below, right? So I have this mg minus t equals the ma, which is this one. So, and of course, in the transverse direction, for this mass over here, right? So there's no any force. Okay. So, and from these two equations obtained by Newton's second law, right? So of course you obtain the same equation of motion from what we have got using the Lagrange equation. Okay. So then let's move on to the next example. Okay, so this one is more complicated, and I will start with a simple case first before moving on to this. Okay, so this is actually an example taken from the textbook of the course, the textbook by Marion. Okay, so and before I actually do this, okay, so let me just remind you of the basics of the pulley system. Okay, so I'm just going to consider one pulley over here. Okay, so this is the ceiling. And then I have a string goes like this, go over like this, right? And then I have two masses, right, which I call M1 and M2. Okay. So, well, this one I believe you have dealt with before, right? So, suppose I have this M1 and M2. If I want to find the acceleration of M1, how do you do that, right? So first of all, by intuition, you understand that if M1 is heavier than M2, then this one will fall and that one will go up, right? So vice versa, right? And let's right. So let's work out the forces, right? So this is the M1G, okay, and then this is the M2G, right? So and of course I have the tension in the string. So the assumption that we make here is that the string is massless, and the tension throughout the entire string is just a constant T, right? So that means if the T over, if here the tension is T, then the over here the tension is also T. Okay, that's the assumption that I make. And right, so now if I ask you to find the acceleration of the system, right? So how do you do that, right? So you just consider the forces acting on the two masses, right? So this is, let me define the coordinate, right? So I will say that the distance measured from here all the way down here, let me call this x, okay? And the other, okay, I'm running out of space here, but the other over here, right? So I call this y, right? And now this force, right? So acting on the M1, right? So for M1, let me write down this M1G minus T. That's the net force, right? Acting on M1 equals mx double dot. And for M2, right? So for M2, very similar, right? So I have this M2G minus T equals my double dot, right? So, and now it seems that I have I told you that I want to find this acceleration M1, so that means I want to find x double dot, right? So, but here it seems that we have the unknown x double dot, and also the unknown y double dot, and also the unknown t, the tension. So two equations, three unknowns. But there is actually one more condition that we have not considered yet. Well, that is again is the constraint of the system. That is due to the fact that the total, I'm assuming that the total length of the string is constant. Okay, it's an inextendable string, right? So that's why, right? So the this part, the length of this part plus the length of this part is always a constant, right? So that is, I can let me just say that x plus y equals L. Right, so that's the fact that the constant length of the string. Okay. So from here, right, so you could find the relation again between the x and y, right? So this is actually very similar to what we do over here, right? So using the fact that the total length is constant, right? So that's why I can say that y double dot, well, x double dot plus y double dot equals 0, and that is y double dot equals minus x double dot, right? So therefore, this one I can just write it as minus x double dot, right? Okay, and now it's two equations, two unknown. You will be able to solve it, right? So for x double dot, okay. So that's good, but now I want to ask a slightly different question. Okay, is that actually let me just work it out. Okay, so I want to find the tension. Okay, so if I want to find the tension, what do? I just add the two equations together. Right, so if I do that, I would have this m1 g plus m2 typo over here. Of course, this should be m1. It should be m2. Okay, so I need to make some correction. So what I would do is actually to take the first equation, okay, multiplied by m2, and then plus the second equation multiplied by m1. Okay, let me do that. So then what I have over here is that is m1 m2g minus m2t plus m1 m2g minus m1t equals the right hand side. What do I have on the right hand side? Is m1 m2 x double dot, okay, minus m1 m2 x double dot, right? So on the right hand side, right, so what I have is just it's just 0, right? So and from here, right, so I can solve for t, and also you can solve for x double dot later on, right? So now, okay, so I want to find the t, not just x double dot. Is because in the example that I'm going to work on, okay, I need both information over here. Okay. So the real example that I'm going to talk about is actually looks something like this. Okay, so I want to basically find out the acceleration. Okay, so the acceleration for all m1, m2, and m3. Okay, so it's more complicated than this one, because now you replace the right hand side to another pulley, right? So and that other pulley further has two masses attached to it. So and okay, again, I will go through both ways. So the Lagrangian and the Newtonian. Okay, but let's start with Newtonian first. Okay, because in the first introduction I also used the Newtonian. Okay. So in this case, right? So all we still need to do is to find out the forces acting on each object, right? So individually, right? So although it looks complicated, right? So but once you consider carefully write out all the coordinates and then consider all the tension and then gravity force, then you will be able to work that out, right? So let's go through them one by one. Okay, so how many objects do we have? So is this M1, M2, and M3, right? And the tricky thing is that now is this pulley also move, right? So if you are moving with this pulley, let's say this pulley is actually moving up or moving down, and if you are just consider that you are yourself is just moving down with it or moving up with it, first of all you will find some acceleration, right? So by this M2 and M3 itself, right? So but then that one is still not the total acceleration of this M2 and M3 because of the fact that the pulley itself, that is this whole system itself, may also be accelerating up or down. Right? So and therefore, okay, so let's define the coordinates in the convenient way. Okay, so instead of just, you can see that from here, I don't define the position of all the masses from the same fixed reference line, right? So for this M1, right, so I use this X. Okay, so this is a fixed reference line. Okay, this is X for M1, that's good, right? So but then for this M2 and M3, okay, so what we do is the following. Okay, so first we use this fixed reference line, okay, so to point to the center of the pulley 2. Okay, so and that describe the motion of this pulley 2 itself. Okay, and then now we take a second reference line over here, and this reference line is not a fixed reference line. It is always moving with the pulley 2, right? And then from here, from this varying reference line, right? So we just point this to M2 and then point this to M3. Okay. So now that's how we define the coordinates, right? And here, right over here, you can already see that we have make use of the constraint. Okay, so this is X. This I call L1 minus X. So meaning that I have assumed that this part plus this part has a total length of L1. Okay. And this I call Y, and this one I call L2 minus Y. And that is, I'm assuming that this length plus this length is always L2. Okay. So once you understand how we use these coordinates, okay, so then what follows should be standard. Okay. So for M1, so let's look at M1, right? So the net force acting on M1, of course, is this M1G, okay, minus this T1. That would be this M1 X double dot. Right. Now for this M2 over here, this M2, I have this M2G, okay, and then this T2 over here, that would be equals to M2A. Okay, so now we need to be careful. Okay, so what is the actual acceleration of this M2? So the actual acceleration of this M2, again, we have to be the observer. Okay, so that is also fixed with this pulley 1, right? So that is, you can see that the acceleration of this M2, I should be talking about the rate of change, the acceleration, right? So I should be using this one as the reference when I calculate the acceleration of M2. And what is this one? This one would be y plus L1 minus x. Okay. So therefore, the MA is M2, the second derivative of this L1 minus x plus y. Okay. That's for this M2. So similarly, okay, for the M3, again, I have this M3G, and then again I have this T2. That is the force, net force, acting on this mass over here. And again, the MA, the mass time acceleration for this M3 is that we need to look at this whole distance over here. And this whole distance is this one plus this one. Right, so that's the second derivative of this L1 minus x plus L2 minus x, y. Okay, so now we have how many equations we have? We have so far we have 3 equations, and how many unknown we have? We have the unknown we have is this T1, T2, okay, x and y. Okay. So that's the we have 3 equations but 4 unknown. Okay. So then we actually have one more equation that is hidden kind of, is that if I just consider the pulley itself. Okay, so this pulley is also doing motion. Okay, so remember this pulley itself is also doing motion. And well, that one is a little bit unrealistic, but I forgot to mention it earlier. But here we assume the 2 pulleys are actually massless, right? So we neglect the mass of the 2 pulleys. Okay, and because of that, right? So if we apply F equals MA over here, right? So what do we have? So the F equals MA for this pulley 2, well, that's as I said, is unrealistic. But if you accept the fact that the mass is 0, so that means m times a is 0. So although it's accelerating, but the m times a for this pulley 2 is actually 0, and that means the net force, acting on this pulley 2 actually has to be is 0. Okay, so now what is the net force acting on this pulley 2, right? So the net force acting on this pulley 2 is actually given by this T over here, which is T1, and then the tension, okay, due to these 2 parts of the string. So that's why I have this T1 pulling it up, right? So, and on the other hand, I have this double of the T2 pulling this down. So that's why this T1 has to be equals to 2 times T2, right? So that the net force acting on this pulley 2 is 0. Okay. Okay, so from there, now we have 4 equations actually, and officially we have 4 equations, 4 unknowns, and linear equations, right? So you'll be able to simplify them and work out the x and y. Okay. So that's how we do it with the Newtonian way. But okay, so of course the key, the emphasis of this course is about the Lagrangian, right? So let's again do it one more time using the Lagrangian, right? So right, so again, right, so we just need to consider force this time, but just the potential energy. Okay. So you can see that the generalized coordinates that we used is the same as what we had just before. Okay, just x and y. So now the Lagrangian, right? So kinetic energy, potential energy. Okay. So the kinetic energy for this one, right? So of course, would be easy, right? So for M1, this is just x dot. Okay. And then for M2, right? So I've explained already, you are going to consider this whole distance, right? So that's why it's the time derivative of this whole distance here. So the M2 will be given by y dot minus x dot. So and then M3, right? So M3 similarly, right? So we need to consider this whole distance, take the time derivative, and you find that it's minus y dot minus x dot. Okay. So that's all we need for the kinetic energy, right? So and then for the potential energy, right? So just the gravitational potential energy. You know that for this M1, right? The U is minus M1 GX. Okay. So why do we have this? Is be careful here. It's not mgx. The U is minus mgx. Okay. So it's because now I am defining pointing downward as the positive, right? So that's why I have this minus over here. Okay. And then for similarly, right? So for M2, right? So the U will be equals to, again, is this minus M2G, the total distance. What is the total distance? This L1 minus X plus L2 minus Y. No, I'm sorry. L1 minus X just and plus Y only. Okay. The L2 minus Y is for M3. Okay. Right. So then now you can see, right? So this whole thing is just the total kinetic energy, right, for the three masses, and then this one is for the potential energy for M1, right? So this one is the potential energy for M2, and this one is the potential energy for M3. So then next, right, Lagrange equation, right? So again, I'm not going to remind you one more time, but just apply the Lagrange equations, right? So you obtain the two equations of motions over here, and then you can actually show by yourself that the y double dot is given by this, right? This is complicated expression, but although it looks messy, but still, okay, this is just a constant. Okay, all the accelerations are actually not varying. Okay, so you can see that it's still just proportional to g over here. So once you work out y double dot, of course you can work out the x double dot. Okay. So let's also finish the last example, and then we'll have a break. Okay, again, this is a complicated one. Okay, so what I have here. Okay, so what I have is, first of all, I have this mass block over here that is free to move along this plane. And then there's a string attached to this point to the bottom of this mass block. And then the other end of the string is attached to another small mass m. Okay. So this is free to move like this, right? So what about this, right? So this one is free to move, free to swing like this. Okay, so this L, suppose I just, okay, instead of having a string, let me say that this is just a rod. Okay, so the length is always L, is a rigid rod, let's say. Okay, so then I want to study the motion of this thing. Okay. So if this mass over here is fixed, of course, this is just what you're familiar with, just the simple pendulum. Okay. But now, because the upper mass can also move, right? So you could imagine that the motion, right? So the whole system is much more complicated, right? So the mass of this can be moving to the right, and then at the same time, this one can be moving to the left, right? So or the whole system can be accelerating to one side, but well, if there's no any external force, the whole system should not be accelerating. But let's say if maybe there's some moment that these two mass may be moving to the right, right? So let's say if you give some initial velocity, okay. So how do we deal with this system? Okay, so in fact, okay, so again, I'll try to use both ways, and the reason why I want to still remind you the process of using the Newton's equation is because from the comparison, okay, so you might start to appreciate that there are many cases that you might find more convenient to use the Lagrangian formulation. Okay, and the other reason is because I want to make sure that we don't just lose all the intuition from what you learn with the Newton's equation. Okay, so here, right? So if I just go ahead and find the Lagrangian again, right? Two things: the kinetic energy, potential energy. So the kinetic energy, of course, means the sum of kinetic energy of this mass and this small mass. So this one, of course, is easy to deal with, right? So because it just slide left and right, right? So the velocity of this big mass is just x dot. Okay. So then the complicated one is the small mass over here. Okay. So how do I write the velocity of the particle? Okay. So first of all, again, imagine that you are, let's say you are moving with the system, right? So by this, so let me just put a virtual box to enclose the entire system, right? So you just imagine that the entire system, right? So including this mass, of course, is moving at this velocity x dot, right? So let's say that this is my reference frame. Okay, so this. So and now if you are moving, right? So if you are also in this reference frame inside this box, right? So what you see first of all is that this big mass is not moving, right? Because the velocity of this big mass is x dot, and now your reference frame is also moving at the same velocity x dot, right? So first of all, then if you are inside this reference frame, then you find that this problem, right, just looks like a simple pendulum with a fixed support, right? So therefore, if you are that person, so what you see for the velocity of this particle, right, is basically just like this, right, just swinging like this. Okay. And remember, what is the magnitude of this? Right, so this is just L theta dot, right? So now, if you are that person and if you want to decompose this velocity, right, so into the horizontal component and the vertical component, right? So you tell me that, right? So this is just simply L theta dot cosine theta, right? Because this is theta, this is also theta. Okay. So And then on the other hand, right, so this vertical component over here is L theta dot sine theta. Right. So this is what you conclude, right? So if you're moving with the system. So now you just need to step outside and go back to the rest the rest coordinate system, right? So and then you just need to the total horizontal component of this particle is actually this term plus x dot, right? This is the actual horizontal component of velocity for this particle. Okay, and that's what I write down over here. Okay, and for the vertical one, you don't need to worry. Okay, so because the coordinate is not moving up and down, so the vertical component is still this L theta dot sine theta. So now I'm ready to write down the 1/2 mv squared for this, and then the 1/2 mv squared for this. Right. So, right, so this one for the big mass, right? So this one for the small mass, right? Okay, and then for the potential energy, okay, so that one is actually easy. Okay, it's just this mgl cosine theta, right? So this considering this vertical distance. Okay. So next, if I just go ahead and try to expand the terms and then do some regrouping. Okay, so this is what I have. So again, in this case, right, so I have two generalized coordinates, right? Is this x and theta. Then of course, Lagrange equation, right? So with respect to x, give you this one. And then the Lagrange equation with respect to theta, give you this one. Okay. So, and this is interesting to note that the first equation, okay, actually equivalent to the conservation of momentum in the x direction. So well, it's not surprising that we have conservation of momentum in the x direction because, okay, so this system, the only force that, well, the forces acting on this system are all vertical, right? So external force, because mg for this one, and then mg for this one, right? And then you have normal reaction force also vertically, right? So that's why no horizontal force acting on this, right? So therefore, right? So in fact, if you actually try to write down the x component for the momentum of the entire system, what do you have? You have this mx dot, right, plus this small m times what I have over here. That is equals to a constant, right? And that is equivalent to this equation. Okay, so if I go ahead and take the derivatives, right? So I will have the two differential equations. Okay. And again, this would be very difficult to solve, right? So they are coupled together, and then there are also some nonlinear term. But we can again consider the small approximations, small amplitude approximation. That is when the theta is small. Okay, so can we make things more simple? Okay. So it turns out we can. Okay, so if we have this theta to be small, okay, for theta to be small, right? So then you learn that, right? So you can approximate this sine theta, approximately equals to theta, and this cosine theta approximately equals to 1. Okay. And then this theta dot square just go to 0. Okay. So then at the end, what you have is that the first equation becomes m plus small m x double dot plus ml theta double dot approximately equal to 0. And then for the second one, you have this L theta double dot plus X double dot plus G theta approximately equal to 0. And then you'll be able to show that let's give this equation over here. Okay. So if you look at this equation and compare with just a fixed a mass over here. So what you have, if you just have a fixed mass, the simple pendulum equation is just this, right? And this one, right? So if we take the limit, you can actually get there, because this one is just equals to 1 plus small m divided by big M, right? And if you take the limit, m tends to infinity, right? So then this whole thing is just 1. And that gives you back the simple pendulum equation. Okay. Okay, I think let's take a 10 minutes break here first. We come back at 10:35. Okay. To resume the recording. Okay. So now let's move on to the part 2. Okay, so move on to the part 2 of this chapter over here. Is that okay? Right. So why is it more convenient? First of all, if we try to think back on what we have done over the several examples that we have, we start from the potential energies, right? So and then we just, after you can write down the potential energy and you take care of all the constraints, right? So and then you are able to just apply the Lagrange equation, right? So without actually worrying about the direction of the different forces, right? So and it seems to be the reason, okay, so why it is more convenient, right? So for example, if I just we call this example over here, right? So it's this particle sliding down on a moving wedge, right? So and for the Newtonian wave, right? So we need to consider all the forces, right, including the normal reaction forces. Right? So in the Lagrangian method, right? So we do consider the potential energy, and of course you understand that the potential energy is due to force, that is gravitational force, right? But the normal reactions, right? So we don't have a potential energy that is associated with this normal force, right? And similarly, right? So when you deal with the problem of pendulum, again, right? So you deal with the potential energy, and that comes from the force that is due to the gravitational force again. But when you write down the potential energy, that is no information about the tension at all, right? So the potential energy terms does not contain any information about the tension. does not contain any information about this normal reaction force. Okay, but somehow, okay, so even without that, right? So we're able to just from that Lagrangian and then obtains all the correct equation, right? So that is, it seems that we have bypassed the need of thinking of this normal reaction force or tension force. I call these forces the forces of constraint. Okay, so it seems that we can bypass it in the calculation, and that's one of the reasons why you will find it much more convenient, right? So to use the Lagrangian. Okay, but actually, right? So you never really actually totally ignore these forces, right? So in your problem, even they are not in the potential term. Okay. Then where are they? They are actually hidden in your constraint, right? So for example, in this problem, okay, so the t, I know that this is t here, and when you work on this problem, right, so you use this data as a coordinate, and then you basically have the constraint that you have already considered, right, which is r equals the total length, right? So the radial position of this particle has to be equals always to L. Okay. So the information of this force of constraint is actually hidden in your constraint equation. Okay. Similar to this one. Okay. Remember that when we work on this problem, right? So the generalized coordinate we choose is this one and this one, right? And the fact that why we know that, so that means when I pick these two coordinates, I have already know that this particle can only slide like this, right? So that's the constraint. And again, why do we have such a constraint? Because of the normal reaction force. Right? So that is whenever we have this problem, and then we have the constraint, which can be also written as an equation. Okay. That constraint equation, okay, actually tells you the information of these forces of constraint. Okay. So then here comes with a new question. Okay, is that now when I solve for this problem, for example, I can solve for x and s, right, without explicitly knowing n. Okay, what if I also want to know n? Okay, for some practical reason, let's say I just want to know how much force is acted on this wedge by this ball. Okay, so then if you just use the Lagrangian mechanics that we just learned, right? So you don't have that information. You're missing something. You don't know. Right? So then you actually have to go back to the Newtonian equations and find this force of constraint. Okay. However, okay, it turns out that in Lagrangian mechanics, okay, we do also have a way, okay, so to actually have obtain the information of these forces of constraint. Okay, and that's the part 2 of this chapter is about. Okay, so that is the using the Lagrange equation, okay, with the Lagrange multipliers. Okay. So then before we work on physics, okay, we need to go back to some math. Okay, just again some reminder over here, right? So I consider a particle moving along the xy plane, right? So you know that the action, okay, is expressed this way. Okay, so and Now, if you don't have any constraint, then you are happy with this. You just use Lagrange equation for x and the Lagrange equation for y, and then you are done. Okay. But then suppose this motion, right, so it's subjected to a constraint. Okay, a constraint can always be, okay, can be the constraint that I consider at least can be written as an equation like this, right? For example, right, for the pendulum problem. So again, I've said this too many times, but this is xy, right? So, but what is the constraint? The constraint is that the x square plus y square has to be equal minus L square has to be equal to 0, right? So that's the constraint, and that can be written in the form like this, right? So that's the example. So previously, right? So whenever we see a problem like this, right? What we do is that we no longer actually express this Lagrangian in terms of two variables, right? We basically know that we just have one independent variable. And then we consider this in the first place. And then instead of writing this Lagrangian in this x and y, we write it as L of theta dot d. Right, so that's how we did it before, right? So we look at the problem, and then we consider the constraints, and then we use the minimum number of generalized coordinates, and also usually the most convenient set of coordinates to express the Lagrangian, and then start from there. Okay. So here we will use a different strategy. Okay. What we are going to do is that, again, right? So I'm considering this problem on xy plane, and then I know that I have a constraint. But in the first step, I just pretend that I don't know about this constraint. Okay. Okay. Or I should say I just ignore this. Okay. So I just still treat my problem, right, as a two variable problem. Okay. I deal with this later. Okay. So then that is, if you want to deal with this, right, so you will just use the same procedure as we had from the last chapter, right? So how to do the calculus of variation, right? So if you have this two variable problem and you don't care about a constraint yet, right? So the strategy, remember, is that I'm going to assume that this x can be written as this x mean plus some parameter eta 1, and then this y equals y mean plus alpha eta 2, right? So this is exactly the same as what you have seen in the last chapter. Okay. So, but in the last chapter, I always have this this formulated as an integral over dx, right? But now we have this integral over the time. Okay. Right. So again, these few lines remind you again exactly the same as what you have seen in chapter 1. Okay. Nothing new. So and what you will see is that same thing applying chain rule, right? So you have this two terms with this eta 1, right? Eta 1 is the variation for x, right? This eta 2 is the variation for y now. Okay, so then I have these two terms over here. Okay. So, and remember the next step is to do integration by part again. This step also exactly the same as what you have learned in chapter 1. Okay, so up to this, you should be familiar already. So, and now you can see that I have these two Lagrange equations, right? So you can see that the Lagrange equation for the x direction, Lagrange equation over the y direction. So far so good, right? So, and if x and y are truly independent, so that means they are not under any constraints, then you can safely say that, okay, this eta 1 and eta 2 can be picked arbitrarily, right, without any correlation. And then what you would have concluded is that because this is arbitrary, And if I want the whole integral to go to 0, so then this one and this one both have to go to 0 individually, right? So that's how you would have concluded. Okay. But now here is the thing, right? So the eta 1 and eta 2 are no longer independent, right? So because of the fact that this x and y has to satisfy a certain relation, right? So that means here when you do variation, if you arbitrarily pick an eta 1, then this eta 2 has to follow the rules, right? Such that after you pick eta 2, the whole thing has to be satisfied this, right? So in short, right? So eta 1 and eta 2 are not independent, right? So due to the constraint. Right? However, okay, so now I want to find the relation between eta 1 and eta 2. Okay. So one thing is that this one important fact is that this constraint equation must be satisfied for any value of alpha. Okay, remember the alpha is this parameter. But no matter what kind of path that you are going to try, or you're going to vary, okay, so they always have to be satisfy this equation. Otherwise, that is not the path that you are allowed to try. So in other words, right? So this whole thing should not depend on alpha, right? So that is it, dg alpha has to be 0. And this dg alpha equals 0, then this, on the other hand, this dg alpha can be written like this, right? So using chain rule. And then remember, and now we have this partial x partial alpha term, this partial y partial alpha term. And this partial x partial alpha and partial y partial alpha can be obtained from these two forms, right? So therefore, this partial x partial alpha is eta 1, this partial y partial alpha is eta 2. So now we have obtained a relation between this eta 1 and eta 2. Okay. And then what I'm going to do next is to substitute this relation, okay, put this relation back to the integral. Okay. So here, right? So what I do is that I express eta 2 in terms of eta 1. Okay. So and then I put it over here. So then this thing is eta 2. So now the nice thing is that I have now I recover a common factor, which is eta 1. Right, so that the whole thing times a common factor eta 1. Okay, so that's the integral. And now I can argue that eta 1 is really arbitrary, right? So because I don't have eta 2 with it now, and this eta 1 is arbitrary, and then if I want the entire integral to be 0, then that means I want all the terms in this bracket to be 0, right? So that's why I write down over here again. Okay, we are almost there. And now from here, I just rearrange the terms such that the left-hand side only contains x or x dot. The right-hand side only contains y and y dot. Okay. So and then next, what I'm going to argue is that well, this one, you know that ultimately x and x dot will be function of time, right? And also y and y dot will be function of time, right? So that is to say, I can say that the left-hand side is equals to some function of t. Okay, and then the right-hand side has to be equals to the same function of t. Okay. So that they are always equal. Okay. And in fact, okay, so I'm not going to call this f. I'm going to call this minus lambda. Okay. So you may still remember we also use the symbol lambda when in the last semester when you learn about the Lagrange multiplier. Okay. So now the left-hand side itself can be one equation, and the right-hand side itself can be one equation. And let's give these two equations over here. Okay. So what you see over here, right? So on the left-hand side, it's just if the right-hand side is just 0, right? So then what you have is the Lagrange equation that you have learned. So but now this is the Lagrange equations, but with the Lagrange multiplier, right? Is that the right-hand side will have this term, okay? Lambda partial g partial x is lambda partial g partial y. And these two are the equations of motions that you need to solve, right? So, but you may ask, so what about lambda, right? So lambda is also an unknown function now, but yes, that is true. But now you also have to go back to consider the constraint equation itself. So now you have three equations now, right? So equation for x, equation for y, and then this constraint equation. You have three equations, and then you need to solve for x of t, y of t, and lambda of t. Okay. So, and this is more complicated to work with. It seems that it's more complicated to work with, right? Compared with what we have done, right? So in the last part of the chapter, right? And but as I introduced already, okay, so the reason why we want this is to find out the so-called the forces of constraint, right? And it turns out that these terms are the forces of constraint. Okay. So work out lambda, and then take lambda partial g partial x, then that would be the forces of constraint along x direction, and that would be the force of constraint along the y direction. So this is just a proof for the special case that we only have two variables, right? So you could imagine that if we have, let's say, if your particle, right? So it's moving along the 3 dimensions. So you could imagine what happened, right? So if I also have the z dimension, then I have the third equation over here. Okay. And now, one thing is that to obtain this equation, right? So this is a simple proof. Okay, so but it can also be shown that if you, okay, so just if you just forget, okay, so forget all the derivation here. Okay, if you start with this, okay, so you can see this small thing over here, right? Okay, so let me write over here. So usually, right, so you just start with this, right? So this is the action, and then you apply Lagrange equation. So with the Lagrange multipliers, so we do this. So, right, so as I said, forget the derivation here first. If I ask you, okay, so if I ask you to minimize this, what do? You do Lagrange equation like this, right? So partial L partial x minus d dt partial L partial x dot equals 0. Okay. If I ask you to minimize this, okay, so what do? Right, so what you would tell me is this partial x L plus lambda t g minus d dt partial x dot L plus lambda t g equals 0. Okay. So if you actually go to expand the terms, right, so you find that writing too small over here. Let me just start a new page. If you actually go to expand the terms, right, so what you would have is that the first one, right, so is this partial L partial x plus lambda t partial g partial x, and then minus this whole term, right? So but this g, I assume that it only depends on x and y, but not x dot, right? So the second term here is still this one. Okay. And that you will find that this is the same as what we have just derived. Right, so this is exactly the same as what we have just derived over here. Okay. So that is, right, so this equation, okay, so can be obtained, okay, so by minimizing this, right? So apply the regular Lagrange equation on this integral. So the reason why I want to talk about this is because maybe this is a slightly easier way to remember things, right? So you want to just remember one Lagrange equation, right? So suppose you just want to remember just one Lagrange equation, which is this one, right? And you don't want to remember, these terms and then maybe the minus sign over here, right? So you just want to remember this, right? So you just need to remind yourself that, okay, with the constraint, okay, I'm not doing L. Okay, I'm doing L plus lambda t times g. So that's just another way that you can memorize this. Okay. So, and of course, you always have to consider the constraint, right? So whenever you solve this equation, you always have to put your constraint beside you and then see when you need to use it. Okay, so now let me just lay out the general case. Okay, so I have a system, okay, described by n generalized coordinates, not just x, y, z, right? So suppose this does not even have to be a single particle system, right? So it can be a multi-particle system, and suppose I need n generalized coordinates, let's say, and I have one constraint, okay, over here. Then now, if you want to solve the equation of motion, right? So this is what you have over here, right? So and there are n equation over here, but plus the constraint equation, right? So you have n plus 1 equation above, right? So and then you need to solve for n plus 1 unknown function, which is all the qt and the lambda t. Right? And as I told you, right? So this lambda t partial derivative times this partial derivatives would be the force of constraint. Okay. And in fact, these are called the generalized forces of constraint. Okay. You understand that why I call this generalized, because if you are not using x, y, z, but you are not using other q as the generalized coordinates, then that's why this is called the generalized force of constraint. Okay. And you might still you might guess that if this is XYZ, right? So this generalized force, well, actually means the force along the XYZ. Okay, but if these are theta, such angle, okay, so then this generalized force of constraint no longer has the unit of force. Instead, it has a unit of torque. Okay. Okay, but then now we might ask, okay, so why does these things represent a force, and particularly why do they represent the so-called forces of constraint? Okay. So here is a heuristic argument just to give you some intuition. Okay, so the formal proof, okay, is beyond the scope of this course, but I'll give you some intuition, right? So I just told you that, right? So now we are minimizing this integral, right? Instead of L, it is L plus lambda times G, right? So we are minimizing this Lagrangian, right? Not minimizing Lagrangian, minimizing the action. So, and now if let me just call this L prime, okay? And this L prime would be equals to L plus this. So what is L? L is the kinetic energy, right? Minus the potential energy, right? So, and then plus this lambda T times G. Okay. And let me regroup the terms. Okay, I'll just regroup the second and the third term. So then I'll just write as U minus lambda T times G, right? I regroup this. So this L prime, okay, so if somehow I still want, right, so the first term is the kinetic energy, no question asked. But somehow if I want the terms here to play the role of potential energy, right? So then, well, first of all, okay, so we understand that the constraint, right? So it's not written as the potential energy, but still, let me just say that, okay, I want this term together to play the role of the potential energy, right? And you know that the force, right? So the force is given by minus partial u partial x, right? If it's in the x direction, right? So now if I just consider this whole thing, right? So I want to take if I consider this whole thing as some kind of potential energy, then and if I take the partial derivative, it looks like this, right? And that would be equals to minus partial u partial x plus lambda t partial g partial x. Okay. So unless and this is the total force, let's say, and this total force would be equals to this minus partial u partial x plus the second term. Okay. So the first term is something that you are familiar with, right? It's it's the force coming from the potential. Then what is kind of not in this term, the leftover things is over here. Okay. And this is the force that are not expressed in terms of the derivative of potential. Okay. And this is the force of constraint. Right. So again, recall, right? So what you have here, right? So potential only talking about the gravitational potential energy, right? And that take care of the mg force, right? So what is not being taken care of, right? So in the potential is this normal reaction force, okay? And that is taken care by this term over here. So that's the force of constraint. Okay. So that's a lot. Okay, let me also finish this example. I know I overrun a little bit, but without examples, it's really difficult to get what's going on. So again, this is okay. I've done this example too many times already, right? So this is the simplest one. Okay, just a fixed inclined plane with this particle sliding down. Okay. So what we are trying to do, right? So now I pretend that, right? So there's no constraint, right? So we know that there's a constraint, that is this plane, right? So but if there's no constraint, right? So the Lagrangian is simply written like this, right? So keep it as a two-variable problem. Okay. And then the constraint equation is written over here. Okay. Right. So so y equals x tangent theta, right? So that's describe this line over here. So now apply what we have learned. Right, Lagrange equation for x, Lagrange equation for y. Right, so but I have this additional term on the right hand side. Okay. So this partial g partial x is just minus tangent theta. Partial g partial y is just 1, given here. Right. So then these two Lagrange equations will give you these two equations of motion. Okay. And then from the constraint equation itself, right? So y minus x tangent theta equals 0. I have the third equation. Okay. So from these three equations, I'll be able to find out x double dot, y double dot, and lambda double dot, right? So, and maybe I don't have time to actually work this out, but I believe you can do it, right? So three linear equations, three unknowns. So, but let's quickly look at what Newtonian's equation would give us, right? So that you actually convince that these two are the force of constraint, which is the normal reaction, of course. So just consider Newton's equation, right? So for Newton's equation, so let me draw this mg, and then this is the normal reaction n, right? So if I consider the x direction, what I have, right? So this is my ny, this is my nx. Okay. So usually you don't break down the two components like this, but because I want to show that how it match with this, right? So but let's do this. So mx double dot would be equals to this one. And then y direction, my double dot will be equals to ny minus mg. Okay. So these two. And now you see, compare this equation with this equation. Okay. So you can see that this nx over here indeed is this term. Okay. And this ny indeed is this term. Okay. Okay. So because this term itself is lambda partial g partial x. Okay. And this term, right? So it is lambda partial g partial y. Okay. So and just try to work it out by yourself. Okay, so if you from the Newtonian's mechanics, so you know that n is mg cosine theta. Okay, so and then nx is mg cosine theta sine theta, right? And then ny is mg cosine theta cosine theta. Try to verify that this one is indeed this, and then this one is indeed this. Okay. Okay, so that's it for today. Okay, so homework due next Friday. Okay. So a couple more examples to go. Okay, I plan to finish this today, but I could not. So we'll come back after the holiday.